Okay, so now that we've learned about probability, let's then now integrate the two concepts of Venn diagrams and probability as well into one. So a question comes, which a usual statement of a question is that a Venn diagram is shown and it says a person is picked at random. So this is the Venn diagram, and let's say the question continues after that in different ways. So a person is picked at random is like the constant statement in these sort of questions. So now let's say I've completed by a person is picked at random. What is the probability that the person is from group A? So we'll see the elements of group A. It is 10 plus 5 plus 7 plus 10. Okay, the favorable outcome, the probability is favorable over total, right? So the favorable outcomes is 20 plus 7, 27 plus 5, 32. 32 over total outcomes, that which are 32 plus 11, 43 plus 9, 52 plus 8, 60. So this is the probability of a person being from group A. You can simplify the fraction if you want to, but let's keep it this way for simplicity reasons. And then let's do another one. If I say that a person is picked at random from group, let's just okay, let's now just complete it again. Okay, so if I say that a person is picked at random from group C, then we'll do P is equal to F over T is equal to 11 plus 9, 20 plus 10, 30, 37 over 60. Right? So what am I actually doing? This can also be written as probability of A, right? And this can be written as probability of C. And this is written because there is no such condition on this question, and I have said that person is picked at random from all these, and it could be anyone, so the denominator is always 60. But what if I impose a condition? If I say a person is picked at random from C, it means that our set is now limited to only the elements of C, which are 37. Find the probability that the person is also from A, right? So now if I have this probability, it could be written as P of A from C. This line, this straight line, shows that the person is from C, and now the denominator will be the elements of C, right? So we can say 37, and now let's count the people who are from A as well as from C. So the people from A as well as C, that is the set over here. This is that set. So we have 10 plus 7, 17. So it is 17 over 37. Okay, so now that we've learned about conditional probability as well, and more importantly, I've played a game. So now let's move to the last thing of this lesson, and that is learning about mutually exclusive, inclusive, and independent sets. Exclusive, mutually inclusive, and mutually independent. I'm saying that again, that feel free to rip my handwriting apart in the comment section. Literally, I know it's the best, like you need not mention it. Anyways, mutually independent, yeah. Okay, so mutually exclusive sets mean the sets which don't have an intersection area. Like for example, if it is an A, this is B, then there won't be an area where the A and B have common elements. Let's look at an example. So in a coin toss, if I toss a coin, there is a probability, a half probability that I'll get a heads, and half probability if I get of getting a tails, right? Provided that it's a fair die. fair coin. So if however I toss a coin, I can't get heads and a tails at the same time, right? So an element can never come and in both A, let's say A is heads and B is tails. An element can never come in both sets. Therefore these two sets are mutually exclusive. Mutually exclusive sets can be represented by probability of A intersection B, which means inside A but inside B is equal to 0, which means that there is no intersection set, right? And now let's look at an inclusive set. And now this is an inclusive set, right? And I can prove this because it has intersection points. Now let's say if I have to see if A and C are inclusive, right? So I'll sketch A, I'll sketch C. I have an intersection point. This is 10, this is 11, and this is 10 plus 7. Let's say I'm assuming that I'm making another question, so I'll give it 5. Okay, this is A, this is C. Now if I look at it, so in this inclusive set it has one property, and that is that the probability of A union C, which means A inside A plus inside C, that probability is not equal to literally A plus C, because if I do probability of A plus probability of C, then it would include this 5 as well, and this 5 would be counted twice, but we have to only count it once. So therefore we'll have to subtract the probability of A inside A but inside C once, because we need it once, right? So if I do it in the numbers form, probability of A is 10 over 16 and 26, plus probability of C is, sorry, it's not 10, it is 15 over 26, because we have the 5 as well. 15 over 26 plus 11 plus 5, 16 over 26. Now this is literally plusing the union thing, but we need to plus the common thing once. So we need to subtract the 5 once, which is 5 over 26, and that will give us the probability of A union C. So this is what is meant by a mutually inclusive set. Now we've done exclusive set and inclusive set. Now let's look at independent set. So let's say if I toss a coin and then I roll a die, what is the probability of getting a 6 on the die and a heads on the coin, right? Now these two occurrences are independent of each other. Let's say if I have a heads on the coin toss, I can still get a 6 on die, and even if I get a tails, I can still get a 6. So this means that there is no effect on each other's probabilities, right? And for such an occasion, we list the possible outcomes. So let's say over here we have die. I'm listing the outcomes of a die 4, 5, 6, and here is the coin heads and tails, right? Now I'm just writing these two together. This is 1H, this is 2H, this is 3H, 4H, 5H, 6H. Now this is 1 tails, 1T, 2T, 3T, 4T, 5T, 6T, right? Now what is the probability of getting a heads, which is this, and also getting a 6, which is this? That is this thing. And now we have one such occurrence, one favorable outcome out of the 1, 2, 3, 4, 5, 6 and 6, 12. So this is 1 over 12. And if we see individual occurrences, we can see that a heads probability of a heads is 1/2, provided it's a fair coin, and if it's a fair die, the probability of a 6 is 1/6, right? And now if I have to check the probability of getting a head and a 6 in independent events, independent occurrences, I can multiply these two and still get 1/12. So this is the same as this, and the outcome of one does not have any effect on the other one. So that is what is meant by mutually independent sets. Okay, now I guess that is it for today. It's a very long video, and for the questions part I'll be uploading shorts for some questions, and if you see my videos directly from the shorts, then I'll reference my video in the short as well, so that you can click on the video and see the entire video and get the entire lesson before attempting the questions. Okay, thank you, bye bye.